Welcome back, everybody. Let's try to go through this relatively quickly. I might take some pauses on this thing too and just write out some stuff. But let's go 1 through 7 on this one right here, you guys, is going to be chapters 5 and 6 review. So let's talk about it. What we have here is number 1 for chapters, like I said, just for chapters 5 and 6. So 5, I don't know how broadly to write this, 5 and 6 review. So this is associated with the review, you guys. Chapters 5 and 6, and it should be seen on the actual, on the film, on the film icons and stuff. All right, so here we go. For number 1, find f, round to 1 decimal place. If they give you all this data, plug it into here. They give you all this data, plug it into here. This is what your calculator is going to spit out for you. They want it rounded to 1 decimal place. So the 5 has a 1 right next to it. Stay a 5, and it's right here. 2, find p. Given all this data, here's the formula for p that you're using. Plug in all that data in your calculator, do it carefully, and you get this. They want it rounded to thousandths, tenths, hundredths, thousandths. Well, that stays a 0 because the 4 is not big enough to bump it up. So you got this. That was 2. 3, find s. V is 120, G is 32.2. S is given by this formula. You will take this formula, plug in these values. It'll spit out this roughly. They want the answer rounded to the nearest whole number, round to a whole number. The 3 gets bumped up to a 4. There you go. 4, find C. Given this data, H and big H and small h, this is what you are using. Plug everything in. It should spit this out for an answer. They want the answer rounded to the nearest 3 decimal places. So 1, 2, 3, okay. Does that stay a 3 or go to a 4? The 9 makes it bump up to a 4. 5, find s, round to hundredths. Take this, put it in here, get the cube root, you get right about here for an answer. They want this rounded to the nearest hundredth. And so the 8, will the 8 bump up to a 9? Well, now with a 2 next to it. So it's staying right there. 6, find f. They're giving you this data, V is this, L is this, and you're using this for problem 6. For problem 5, you were using this, guys, as well. And again, it should be pretty obvious when you look at the actual review exam that you're talking about. Take these, do the division. I actually did this divided by that and got 0.66622 something. And I did this divided by that and I got 10 to the 5th. Well, I took the 0.66622 something and made it 10 times bigger. So I got to make 10 to the 5th 10 times smaller. So you get this. If you round this, I think they're asking, round this to 2 decimal places. This right here, is it going to stay a 6 or go up to a 7? Well, the 2 right next to it's going to keep it right where it's at. So it's this right here. 7, it's a little bit of an interesting situation here. All things considered, the temperature remaining constant across both scenarios, the broadness of the wire remaining constant across both scenarios. So the thickness of the wire and the temperature, so the thickness of the wires are the same, and the temperatures in which the 2 wires find themselves are the same. The difference here, and the only differences between the 2 wires being compared, are going to be the lengths. Typically, the longer a wire is, the more resistance to the flow of electricity is associated with it. A long wire is going to have a harder time conducting electricity than a short wire is, all other things equal. Directly proportional to that. So if the wire is 100 times longer than some other wire, then it's going to be 100 times more difficult for electricity to flow through it. There's going to be 100 times the resistance. So what they're saying here is, if there is associated with a particular type of wire, the resistance of a 1-foot piece of number 0000 aluminum wire is 8.04 times 10 to the negative 5 ohms. What length of wire has 1 ohm resistance? Find round to hundreds. So 1 foot, a 1 foot piece of number 0000 aluminum wire, a 1 foot piece has 8.04 times 10 to the negative 5 ohms resistance. The Greek letter omega for ohms, resistance. For every foot. Well, how long would the wire, that same exact wire, have to be with the same cross-sectional area? We're not changing temperature, we're not changing cross-sectional area. If it's the same exact material, same exact circumstances, same exact thickness of wire, but it's just going to be a longer wire, if it's going to be a longer wire, how long does the wire have to be for the resistance not to be this much, but much more than that, to be 1 ohm? Well, the way you can set that up, there's a number of ways you can do it. You could take the 1 ohm and divide it by this. 1 ohm divided by that, and it'll be that many times longer than 1 foot. It's pretty big numbers here. Do cross multiplication, get down to here, solve for the x. That's going to be the length of a very long piece of wire that's going to have 1 ohm resistance associated with it. That's a whole lot more than 8.04 times 10 to the negative 5 ohms. Do this, get down to here, you're doing this ratio, and you're getting 12,437.811 feet. Round that to the nearest 100, you get this, 12,400 feet. So that is 1 through 7. Pretty quick look at it, but I wanted to kind of give you that look to get there. Let's see how we can move on this stuff, guys, to make it work. I may turn this stuff off a little bit and kind of do some stuff, and we'll kind of take it from there. Let me think how I'm going to do it, guys. I might just put a pause on this thing real quick. Let me maybe just do a couple before I put a pause on this. All right, so we got this. Let's keep going. Okay, guys, let me put a couple up here and then maybe put this on pause a little bit. Put a few more things on here and we'll figure this out. It's hard to know the most efficient way to do some of this stuff sometimes. Okay. For 8 and 9, they're kind of playing the same game with us. And we'll figure it out. For 8, they're saying find M. Round to hundreds. Well, they're giving you big M 1.82 we got this. Let's see where this thing's going to go. Well, I mean, you're doing the same basic thing that we tried to talk about last time, and see how it plays out. What you do is you got to be very clear with the computer, called the calculator, whatever kind of calculator you're using, and figure out what's going on here. Well, I tell you what, I'll take the 32,600, that right there, and divide it by the quantity. It's good to kind of visualize it like that on the calculator if you're going to do some of this stuff. Take the 1.82, square it, and subtract 1. Again, extreme caution with this because you don't know. There might be an issue. There probably should not be an issue. And let's see where the whole thing goes out. I'm getting, that's kind of an interesting thing what I'm getting here, right? I'm getting 14,097.9069. Forgive me, yeah. 14,097.9069. Now let's see if, and again, the calculator, you got to be extremely careful with that. So maybe it's better to take f squared minus 1, do it separately, write it down, and then divide it into 32,600. I think it's going to, this calculator should behave well, and unless there's brackets or parentheses, it's going to follow the order of operations quite well for us, and it should be fine. For 8, the answer is 14,100 because they're saying round to hundreds. So 14,100, here the hundreds place. Does that stay a 0? Does that stay a 0 or go up to a 1? It certainly goes up to a 1. So that's fine. We're good. Let's see, 9. Just make sure here, guys. I'm always trying to check this stuff out. Yeah, 14,100, right, rounded to the nearest hundred. Find W, round to hundredths. So this could be, again, you just have to be extremely careful here. Find W, round to hundredths. N is 860. H is 43. R is 18. P is 56. W is looking like this, which is quite convoluted, I guess you could say. But we can do it. See what's going to happen, guys. See where we're going to go with this thing to get some kind of a value that's going to work for us. So what we have here, well, there's a lot of ways to go. Like I said, let's see how this wants to behave itself. It probably behaves pretty well with the calculator if you're careful. The top is 2 times n. Well, put 2 times n, 2 times that, you get 1,720. Then you're going to divide by a whole array of items. So let's see how we go here, guys. You're going to divide by, you got to put multiple brackets or multiple parentheses here just to play it safe. R, H minus R, the H minus R here. H minus R is 43 minus 18. That should be 25. So this is a little easier than I thought it would be, guys. That's 25. The P minus R is 56 minus 18, right? And that's going to be 38. Let me see here exactly what we're doing. Yeah, I might have been overly meticulous with this. The numbers were much easier to deal with than I thought they would be. Let's try that again. It was definitely easier than I thought it would be. It was so easy that I got it wrong, right? I mean, let's see here. 2 times n is going to be the 1720. Forgive me. 2 times n is going to be 1720, divided by, and it's not a bad move the way this goes. This is going to be 18 times h minus r, which is 43 minus 18, which is 25. And that, again, that turned out a little easier than I thought it would be. And then p minus r is 56 minus 18, which is 38. And that's a pretty good number. It's 0.1005848. I mean, there's different degrees of accuracy here on this. Want to do this. Now, what they're asking us to do here with this is round to hundredths. That's the hundredths place. Wow, not much going on there. I mean, so what you got here is 0.10. So there it is. Make sure again, always double check your work, guys. If it doesn't, so the calculator is going to tell you if you make a syntax error, which is what I had the first time I did this. But we should be coming out to something like that. That's number 9. Round it to hundredths. Yeah, that's fine. It's looking real good. 0.10, actually. Looking good. They say some stuff here. We just got to remember what the actual, we can look up the conversions and kind of take it from there. They talk about how are you going to make 12,320 yards? How are you going to make that into miles? 11, 15 grams into hectograms. Hundreds of grams. Well, then you got to make it 100 times smaller. We'll get there. 12, 20.6 centimeters. And there's different conversions, guys, different degrees of, depending sometimes on the textbook as well. 12, 13, 9 meters per second, kilometers per hour. 9 meters per second, convert that to kilometers per hour. (14) 100 degrees Celsius, convert that to degrees Fahrenheit. And picoseconds to microseconds. That's kind of a little bit of a convoluted one, but we can do it. 7,500 picoseconds, make that into microseconds. Micro is 10 to the negative 6. Pico is, I think, 10 to the negative 12. But we'll have to look at that to be sure. I think nano is 10 to the negative 9. All right, as we look at it, let's kind of figure out where it's going to go. Every mile has 1,760 yards in it. So you can set this up as a proportion, or you can simply just take by the conversion factor, miles over 1,760 yards. The yards cancel. Basically, every time you have 1,760, every time you have 1,760 yards, every time you have 1,760 yards, you got a mile. How many times are you able to find 1,760 yards in here? Every time you do it, you got a mile. So you can just take 12,320 and divide it by 1,760 and see how they want to do it. So what we have here is 12,320 divided by, the cancellations are straight, 7 right off the bat. So the answer there is 7. for this guy. You're just dividing 1,760 into the 12,320, and you're there. And that's kind of the way that played out. Hectograms are 100 times bigger. A hectogram is 100 times bigger than a gram, so you need 100 times less of them. 100 times less than this is 1 over 2 over. Divide this by 100. You don't need as many of these when the denomination is really big. You need 100 times less of them, and you end up getting this. And that should be it. Let me make sure I read that correctly. But you got all that. You got this right here. You got this right here. That was, what was that? Number 10, right? Number 10 was 7. 0.15 is this one right here. Absolutely. Absolutely right. Let's keep going. With 12, they're saying go for the inches. So, well, 2.54 centimeters for every inch. So, every centimeter, every inch is associated with 2.54 centimeters. So if you actually do it, you're basically doing 20.6 centimeters, 2.54 centimeters. That's an inch. 20.6. Every time I find, for 20.6, every time I find 2.54, I've got an inch associated with it. So 20.6 divided by 2.54, right, 20.6 divided by 2.54, 20.6 divided by 2.54, 8.11024. So 8.11024 inches. Now, what do they want? How do they want this reported? They want it to the nearest, I think they want it to the nearest 100 when they're doing this. Let's have a look here. They're not really specifying, so I guess we'll do what we have to do. They took it. I mean, if they're not specifying, I can probably be pretty generous about how I'm going to look at stuff, pretty reasonable about it. But they got 8.11 for a final answer. They're round, which is fine, which makes perfect sense. I mean, this is 8.11, it's the nearest 100th. It ain't going to go any more than that. It's way closer to this than to anything else. So you got this. .11 inches on that. It can get a little more convoluted because there's other things you're doing to make this happen. How are you going to convert meters per second to kilometers per hour? It's a good question. Well, I'll tell you what I'm going to do. The way I'd play the game with this thing is, I remember that 1 kilometer is 1,000 meters. So basically, the special one is 1 kilometer over 1,000 meters. Or I can also write it as 1,000 meters over 1 kilometer. Depends on what I want to do. If I want kilometers on top, I'm not going to go 1,000 meters over 1 kilometer, though that is valid. This is valid. Because of this, you can write two different ratios. 1 kilometer over 1,000 meters, or you can write 1,000 meters over 1 kilometer. I want kilometers on top. I'm going to use that. I also know that there's 60 minutes in an hour, and there's 60 seconds in each minute. 60 times 60 is 3,600 seconds. 3,600 seconds is equal to 1 hour. Well, since I want to get hours, I'm probably going to put the hours on top and have 3,600 seconds. So that's pretty interesting. The two keys are this and this. And if I multiply it right, I should be okay. So I'll tell you what I'm going to do. If we're looking to have this guy be under control pretty well for us, let's see what we can do. I can always start erasing some stuff too, guys. It looks like I'm going to run out of room pretty well here. But let's see what happens here. I'll take 9 meters per second for 1 second. I'm going to multiply. Actually, I want hours on the bottom, actually. This is fine, but this one's better. 3,600 seconds per 1 hour. I can use either one depending upon what I'm being asked, but this is the one to use because I want hours on the bottom. I want hours on the bottom, and so I need the kilometers on top. Right here is kilometers on top, but I need hours on the bottom. So if I want hours on the bottom, I got to have hours on the bottom here. Okay. Watch out for that. Watch out for that. So keep that one. You can go a whole bunch of ways here. Well, I'll tell you what. Every 1 kilometer is associated with 1,000 meters. And every 1 hour is associated with 3,600 seconds. That is the most important aspect of this entire thing right here, guys. If you're going to do this, you're going to multiply this out, and it's going to happen for us. That's where we're going to go. Now let me erase a couple things. I'm going to have to move around a little bit. There it is. So let's do it. Seconds and seconds cancel, hour stays. Meters and meters cancel, and kilometers stay. I'm going to multiply 9 times kilometers times 3,600, and I'm going to divide it by 1,000 times 1 hour. So what we end up getting is, we get 9, well, I'm just multiplying right across, 3,600, and that's going to be associated somehow with kilometers. And then on the bottom, I got 1,000 times hours. Okay, it's a little bit of a mess, but not too bad. Put 1,000 in here. Maybe we can shorten this up without going for a calculator. Put 1,000 in here, you get 3.6 per 1 hour. Do the multiplication here. There's a shortcut to this. It's 36 minus 3.6 is going to be 32.4 kilometers per hour. Again, do the calculator. A lot of what I'm going to try to show everyone a lot of times is before you even go to a calculator, try to get a gut feeling for what's going on here. Try to get a gut feeling for what's going on here. This is number 13. Problem number 13 is going to equal that. 32.4. And it is. Indeed it is. 32.4. So that's associated with that, you guys. That was, right here. For number 13. What that's going to equal. Equals, as we said, 32.4. All right. That's that. That was 13. 14 is this. Again, I'm probably going to have to erase some stuff, guys. But let's see how it goes. How are we going to handle this guy? Well, this one right here is neat, is interesting. Is very interesting. There is a conversion associated with these guys, and that's, again, I guess at some point some of these things have to go. last two from that part here in a second. Okay, well, look, there's some interesting formulas that are out there. Let's talk about them. You want to convert to Celsius? You go 5/9 times the Fahrenheit. If you want to convert to Celsius, you go 5/9 of the quantity Fahrenheit temperature minus 32. If you want to convert to Fahrenheit, you go 9/5 the Celsius temperature plus 32. You take 9/5 times C, get an answer, then you add 32 to the answer. At the very end, you add it. So either one of these work. They can be, they work good. What we need here is we're trying to get Fahrenheit. Well, if you put 100 in here, 9/5 of 100 is 180. 180 plus 32 is 212. 212. All you got to do is put the 100 in here. 5 goes into 100 20 times. 20 times 9 is 180. 180 plus 32 is 212. Boiling point of water, 100 degrees Celsius, 212 degrees Fahrenheit. Okay? Now, let's talk about 15. Actually, not a very difficult move, conceivably, but let's be careful with it. Pico is 10 to the negative 12. 10 to the negative 12 and micro, so micro is associated with 10 to the negative 6. Pico, the way it's associated, I should probably spell it out, pico, P-I-C-O, is associated with 10 to the negative 12. I think nano is 10 to the negative 9. So let's go with that. I guess we'll see shortly what's going on. When you say 7,500 times 10 to the negative 12, that is the same as 7.500. Make this thing 1,000 times smaller. You make that 1,000 times bigger then, so it becomes this. How are you going to get it to look like 10 to the negative 6? You got to make that 1,000 times bigger, but if you do that, that's got to become 1,000 times smaller. So it becomes 0.0075 times. So that's basically 0.0075 microseconds. And there it is. Now let's make sure I didn't look in the book, and we're going to have the book for us, or at least we're going to have a chart. But I think we're okay. For number 15, yeah, there it is. So those are the good assumptions to make. Yeah, this is what's associated. That's associated with pico. That's associated with micro. Pico is this. Micro is this. And there we go. Fantastic. For number 16, they say a few things. We'll try to talk with them and figure out what's going on. So let me just erase this right now, and we'll see what we can say about it. All right, let's see what we can say here. They're giving, and we'll talk about more of this stuff in person. various courses, this gets emphasized a lot more than others. But as we're looking at this, just give you kind of a quick rundown as what's going on here. You got 16 for the 5 measures below. Exact values we pretend are exact values. Whenever measurements are taken, there's an ambiguity. There's the possibility of error. So there's different degrees of accuracy, different degrees of precision. If it's exact, if it's an exact situation, then that's it. It's exact. It's not really an error that comes into it, if we know something's exactly as is. But when you're doing measurements, that doesn't work out that way. There's different values of precision, different values of accuracy to get something like that. They want the greatest, the greatest precision, the least precision, the greatest accuracy, the least accuracy. When they're giving, I mean, at this point, they're talking about, what are they talking about? They're talking about grams, so they're talking about something. So you got this, you got this, you've got this, 54.96. You've got 18.705. So it's the same kind of item here. They're talking about grams. So the unit's not going to be an issue because with the same units for everything for these 5. What has the greatest precision? The greatest precision has the most decimal places associated with it. So that'll be this guy. The greatest precision, and you'll see this in the write-out of it, greatest precision has this. The least precision has the least decimal places associated with it. That's this. The greatest accuracy is, well, if it's a real big number that goes out a lot of decimal places, that's probably going to have the most accuracy. Because you go like the 18.705 is way out there. So at the 10,000ths place, there's an absolute error of 0.0005 over this guy. None of these are going to kind of, they're not going to come, well, they come relatively close. But this one, if you do that, if you take for this guy, 1, 2, 3 decimal places, go a 4th decimal place. 3 decimal places, go a 4th decimal place. That's the absolute error. And divide it by 18.705. That ratio has the smallest value of any of these. You say, what about this? Well, this isn't that big to begin with. You're dividing a small number into something that's roughly, it's going to be smaller, but it's just not going to be enough to make this thing work. You'd almost think this would do it. It's huge. Yeah, I know, but it's 0.05. It's something like 0.012, second place. 0.05 is the absolute error over 725.7. That's still going to be smaller than this. This one's going to be the biggest of all of these. And, it's going to be it's going to be the smallest of all of these. It's going to have the greatest precision, or forgive me, the greatest accuracy. So I'm going to write it as 18.705. The least accuracy, well, you're almost thinking this one, because if you actually do the ratios, because yeah, it's a real small thing, but you're dividing by a real small thing. 1, 2, 3, 1, 2, 3, 4. This guy is 0.00005. Yeah, but you're dividing it by something pretty tiny. So this guy might be an issue. The other ones are pretty fine, but if you actually got to compare all the relative errors compared to the original size of it and see where you are. Yeah, in fact, they do go there when you go with that one. It's 0.0310G. So, for number 16, we are saying that for the 5 measures right here, you guys, for the 5 measures right here, The greatest precision, most decimal places, right here. Least precision, least decimal places. Greatest accuracy, the relative error divided by the size of the initial measurement. That gives you the smallest ratio of all. That's got the greatest accuracy. This accuracy right here is quite small. The greatest accuracy, the least accuracy, it doesn't have a lot of accuracy because that's actually a big number, believe it or not. It's kind of weird that you think that, but you actually do the ratio, it comes out to a bigger answer than any of these. So that's 16. 17 and 18, the numbers below are measurements. 17 and 18, the numbers below are measurements. Perform the indicated operations and report your answer in the correct form. That's 17. 18, the numbers below are measurements. Perform the indicated operations and report your answer in the correct form. Okay, basically, guys, you're honoring the fact that there's 3 decimal places of precision, and you pretty much keep it at that. It's also consistent with what significant figures are. So let's see how that plays out. So what do we got here? That would be, so 17 and 18. So they got these. 17 is saying 0.712 plus 0.850 plus 0.0564. And on the other, that's that one. The 18 is saying take 5.819 and divide it by this product. That's a good amount of decimals, but the other one's not. The other one's actually 2 significant figures. The final answer is going to have 2 significant figures in it. This right here will keep, this is too many decimal places. 3 will work, 3 works, 3 works. When you add it together, for 17, you're going to honor that, and you get, you always round, and if you get something beyond that, you're still going to do all the round-offs, but you're going to round it off to this place, and you're done. Okay? So you got this, and for 18, it's going to be 2 significant digits that you're going to take this thing to when you do it. Go 5.19, 5.1, forgive me, 5.819, 5.819 divided by that product, $1.42748, 1.427, 1.42748, 5. Yeah, 2 decimal places is what's going to rule the show on that. Is that going to stay a 4 or go up to a 5? Just going to stay there. So it's going to come out to 1.4 for that. 19, 20, and 21, guys, and we're done. I'm going at a pretty good pace on this. 19, 20, and 21. Let's do it like kind of old school mathematics when we do some of this stuff. They're telling you use the program in your calculator. Different calculators can do different things. They're all going to give you the right answer. If you got the right calculator, you can do it right, correct? Same with a computer program. Use the program in your calculator for compound interest. Run the program and enter the following values. What is the value displayed for A? So that's 19, and then there's some other stuff here, and they'll go really fast. I think something you got to look at is the way this thing comes out of here is for a problem like 19, let's just kind of do it old school. Let's say that P, the principal, is 5,500. number of compoundings in a particular period of time per year is 12. The rate is 6.8%, which is 0.068, right? Convert the percent. You can't really, I mean, a computer program might do it for you, but when you're doing a calculator old school, you cannot use percents. You got to make it into a decimal. And the number of years, some places call that time, is 16. So you're basically looking at a situation, if you're really going to go old school with this, the final amount is going to be the principal, 1 plus r over n, nt right here. That's big. That helps a lot. It's a lot of fascinating mathematics that goes into deriving this. A lot of fascinating mathematics that goes into deriving that, and that's what you're using. What is that going to be? Well, it's going to be A is A. The principal is 5,500. 1 is 1. 0.068 is the interest rate. I call it small r. They're calling it big R. The number of compoundings they call big N. I'm calling it small n. The number of compoundings is 12. Or is it? Yeah, and the number of years is 16. That's pretty amazing. So quickly, shoot that, let's look at it and see what it does really quickly. As a final answer on this thing, let's see what we can do. I will take the quantity 1 plus 0.068 divided by 12, and I'm going to take that to this. It comes out to 144 plus 48, that's 192. So 192 times 5,500, 16,275. 16,275.76224. 0.76224. Wow, you invested $5,500. Yeah, you invested for a long time though. You invested for 16 years. You invested for a total of 16 years, and it was being compounded monthly. Every month there was being a compounding per year. 12 compoundings per year, that's monthly compounding. Wow, that's a lot. Yeah, you had $5,500, now you have 16. You had $5,500, now you have 16,275. And there we go. They gave us exactly the answer that we got. It's good to know why this is true, how this works. It's really good to know that. So, yeah, pretty fascinating stuff. It's good to know this old school. There's great mathematics that proves this using the exponential function, using that number e. Just two more short problems, guys. They basically are asking you, this is just with the calculator, just telling you what to do with this. 20 and 21. For 20, they're saying select one of the viewing rectangles that gives the best complete graph of y equals 2x plus 19. Again, you want something that's decent size to be able to do that for number 20. So they're saying with that one, they're saying the option C, which is, negative 15 to 5 to negative 5 to 25. So not a real big deal. Let me just, give me 1 second, guys. So guys, okay, so I've got a great coworker who's helping me out very much, so I needed to make sure everything was okay. They're always giving me, the person's always giving me a lot of extra time to do a lot of things, so it's wonderful that we have him working for this great university. So we got this right here. So for 20 and 21 guys, it should go pretty straightforward. You're not gonna make a huge deal out of it. The best window there is, I guess, I guess it's kind of debated. It's almost debatable. They're making the claim here that it would be C. And as you see the thing scroll, I'm not going to spend a great amount of time looking at that. We can look at that in a number of ways, but you would think there'd be a good. It's good that you got a Y min and a Y max that are pretty comprehensive. You could argue this arguably a number of ways, but we're not going to worry about that too much. As far as 21 is concerned, so they're telling us just look at C, and that'd be about right. And the real big thing is, guys, do you understand that this is a linear equation? Can you work with it in relation to other linear equations to solve a system of linear equations, two equations and two unknowns? Can you look at how this relates to something in the physical world? How would you graph it? You'd do a T-chart. How would it look? It's a positive slope. It slopes upward to the right. There's a lot of things we can talk about. There's your y-intercept. Where's the x-intercept? Well, that leads into a pretty neat question. If you look at problem number 21, you use the zoom, get all this stuff. They're saying x-intercept. I'll tell you what I'm going to do. Let me stay off the computerized stuff right now, and let's just look at this pretty old school like we did over here and got a real great answer here. And like I said, I cannot emphasize the importance of the exponential function, of the number e, how the number e behaves, and how using the exponential function you can talk about compound interest. You can talk about, here you're not using the number e right here, but you could if you were instantaneously compounding interest. Here you're not instantaneously compounding interest, you're compounding it once a month, but you're still using a different kind of exponential function. But fascinating mathematics. And again, if you take it to the limit where there's an infinite number of compoundings, you do get e to the something, the exponential function where e is the base of the natural logarithm. That's not happening here, but it could happen if the compoundings became more and more and more. They would approach something associated with an exponential function. But this is fascinating in its own right, and you do exponentiation and get the answers that we got. As far as 21 is concerned, they want you basically at the end of the day, you guys, at least for our purposes, determine the value of the x-intercept. So if you're talking about this right here, the value of the x-intercept, y is going to be equal to 0 if you're looking for the value of the x-intercept. So you got this right here. Add a -3 on each side, and add a -3 on each side, and you got this. Multiply by 3 on each side, and you got this. Divide by 2 on each side, you got -4.5 for the x. The y value is equal to 0 because we're talking about an x-intercept. The height of the graph is at y equals 0, and this is the y-intercept. Forgive me, this is the x-intercept. Okay, guys. I had to go pretty fast on this one, but we did, and I thought it was good that we did. It's got to be done. And that'll be it. I'll see you guys soon. Take care.